Okay, welcome everyone to this seminar. It's a great pleasure to have Tyler Ellison as our speaker today. Tyler has been working at the interface between quantum matter, quantum information, and he is an expert in topological quantum computation and the topological phases. Personally, I would say Tanner was one of the first people I learned high form symmetries from. When I just started being a postdoc at Perimeter, Tyler was a exchange student, exchange graduate student. At that time, I didn't know much about high form symmetry, and he taught me a lot. Today, he's teaching us more about his recent work on universal quantum computation with group surface codes. Tyler, please go ahead.
Thank you, Lucian, for the very kind introduction. Thank you also for the invitation to be here. And also, thank you for sending a reminder email about the talk. I had it in my calendar for tomorrow. So if it feels like this presentation could use about 1 day extra preparation, you're probably right. Well, going to talk about some very recent work with Naren Manjunath, my student Vieri, and Apurv Tiwari. This work will come out very soon. In fact, it'll come out in about an hour. So it's almost like I'm giving a lecture and I'll post my lecture notes afterwards. This is a talk on quantum computation, so let me start with some boilerplate quantum computing motivation. Oh, I need to be able to switch sides. Okay. So we know that quantum computers have the potential to simulate complex condensed matter systems, aid in solving the electronic and nuclear structure problem, provide solutions to network optimization problems, break RSA encryption, and just generally revolutionize science and technology. There's one catch, and that's that quantum systems are inherently susceptible to noise from the environment. The components are small, and you have to deal with quantum errors. Fortunately, there's a solution, and that solution is to use a quantum error correcting code. What this means is you use many qubits or qubits to encode or store a small number of logical qubits. There are many quantum error correcting codes on the market. One of the most promising quantum error correcting codes is the so-called Z2 surface code. What makes the Z2 surface code particularly promising are that one, it has high error thresholds, so it is relatively robust to errors. Two, it is scalable, meaning adding more qubits give you better protection for the information. And third, it's fairly easy to implement. And instead of articulating the sense in which it's easy to implement, I'll just flash three semi-recent experiments which have realized the Z2 surface code in superconducting qubits on a neutral atom platform are trapped ions. So the Z2 surface code is great at protecting our information, but it comes with a catch, and that's that although it is hard for the environment to access the information, it is also hard for us to perform operations. We've smeared this information out across the qubits and qubits. So it's hard for the environment to access it, but now it's also hard for us to access it. Nonetheless, there are some operations that are easier to perform on the Z2 surface code than others. I'll refer to these as native operations. These are operations that can be performed while maintaining the protection of the quantum information in a Z2 surface code. So here are the set of native operations for the Z2 surface code. First of all, there are gates that we can perform, or unitary operations that we can perform on the logical information. And the set of gates that we can perform natively are the so-called Clifford gates. These are the set of unitaries such that if you conjugate a Pauli operator P by the unitary, you get out another Pauli operator Q. So these are unitaries that map Pauli operators to Pauli operators by conjugation. There are also a number of measurements that can be performed natively in the Z2 surface code. In fact, we can measure any Pauli operator or product of Pauli operators in the Z2 surface code. Together, these gates and measurements constitute the Clifford operations. Clifford operations are fantastic. We definitely need those for quantum computing. However, they are not sufficient for implementing arbitrary operations or for performing universal computations. These Clifford operations can be efficiently simulated on a classical computer. For universality, we need something non-Clifford. We need to supplement the Z2 surface code with a non-Clifford gate or a non-Clifford state. And here by a non-Clifford state, I mean a state that cannot be prepared from an all zero state using Clifford operations. There are a number of strategies for supplementing the Z2 surface code with something non-Clifford. The most well-studied is magic state distillation. It's not really important for this talk what is meant by magic state distillation, but what is important is that magic state distillation is notoriously resource intensive, and by some estimates, constitutes the majority of the overhead in the quantum computation. Another approach is dimensional jumping. This is where we take information stored in Z2 surface codes, transfer it to a code in a higher dimension, perform a non-Clifford operation natively in this higher dimensional code, then transfer the information back into the Z2 surface code. This could work. It's a viable avenue. However, it does require that your architecture is able to accommodate three-dimensional quantum error correcting codes. In this talk, I'll focus on a third option, which is using non-abelian topological order to perform the non-Clifford operations. Now, typically when people talk about non-abelian topological order in the context of quantum computation, they have in mind creating quasi-particle excitations or anyons, storing the information in some internal space, and then braiding those anyons to perform the quantum computations. We'll actually take a different approach to using non-abelian topological orders to supplement the Z2 surface codes. So here's the overall strategy. We'll start with our information stored in the Z2 surface codes, and we'll perform Clifford operations natively with the Z2 surface codes. Then, whenever we want to implement a non-Clifford operation, we'll transfer the information from the Z2 surface code into a non-abelian topological order. For this talk, it'll be a G surface code, which I'll introduce momentarily. Then within the G surface code, we'll perform our non-Clifford operations. We'll spend as little time as possible in the G surface code, then transfer the information back to the Z2 surface codes. Now you could ask, why don't we just spend all of our time in the G surface code in this non-abelian topological order, perform all of our operations there? Well, there are potentially two downsides. One, it may be harder to implement the measurements that are needed to operate the non-abelian quantum error correcting code. Second, the decoding problem is likely more challenging. The algorithm for cleaning up errors that as they occur is more complicated for these non-abelian topological orders. So you might as well just spend as little time in those codes as possible. This paradigm isn't new. We didn't come up with this. Here's a non-exhaustive list of papers that have come out use this paradigm of switching between Z2 surface codes and non-abelian topological orders. You notice there's one all the way back in 2018, and the last are just within the last year. Here's the outline for the talk. I'm going to start by reviewing the Z2 surface code. If you're familiar with the Z2 surface code, you can think of this as just setting notation for group surface codes. I'll then describe a set of elementary logical operations that we can perform in group surface codes. We'll compose these elementary logical operations to perform interesting logical operations in the group surface codes. I'll then show that we can bring this story from a spatial picture to a space-time picture, This will give us space-time building blocks, which we can glue together to perform our non-trivial operations. I'll give a few examples and conclude with some future directions. Before I jump into the Z2 surface code, let me just take a moment to encourage questions and comments throughout the talk. I wasn't sure what the audience would be like, so my excuse is for making this as broad as possible is that I'm going to encourage you to interrupt if there are any questions. Are there any questions so far? Yeah.
I have a quick question about the definition of a surface code. Does this imply the open boundary condition, or you still use the torus geometry?
So here's how we'll define the Z2 surface code. Yeah, it's rough and smooth boundaries.
I see. So, and for G surface code, is the
Yeah.
smooth and rough boundary the same, or you need to choose different geometry?
Yeah, good question. We'll get there. Let me build up to that through Z2 surface codes. But yeah, but specifically what I mean is a patch of Z2 topological order with rough and smooth boundary conditions or a G quantum double model with rough and smooth boundary conditions.
Yeah, thank you.
Any other questions before I move on? Okay. So the Z2 surface code is defined on a square lattice with rough and smooth boundary conditions. Rough here just means these edges end. And on each edge, we'll place a two-dimensional Hilbert space, a qubit. The basis for this Hilbert space can be labeled by 0 and 1 states. And the key operators on this Hilbert space are Pauli X and Pauli Z operators, X and Z squared to the identity, and X and Z anti-commute. The code space where we'll store quantum information is defined implicitly in terms of a set of stabilizers. There are two types of stabilizers. First, for the vertex stabilizers, these are a product of Pauli X operators around a vertex. Note that we've truncated this product of Pauli X operators along the smooth boundary. There are also plaquette stabilizers. These are a product of Pauli Z operators around a plaquette or a partial plaquette on these rough boundaries. The code space where we'll store information is defined as the set of states which are stabilized or invariant under AV and BP. And you can check, I'll prove this more generally for group surface codes in a moment, that the code space has dimension 2. Let me now move on to group surface codes. Again, we'll have rough and smooth boundary conditions. I'll implicitly assign an orientation to each of the edges. Horizontal edges are oriented to the right, vertical edges are oriented upwards. On each edge, we'll place a G-dimensional Hilbert space, where G is the order of the group. And because the Hilbert space has dimension G, we can label a basis by the elements of G. I'll introduce two operators here, LG and RG. LG acts on a basis state by left multiplication by G. RG acts on a group basis state by right multiplication by G inverse. It's G inverse here so that RG forms a homomorphism. RG times RH is equal to RGH. Similar to the case of the Z2 toric code or surface code, we can define a code space implicitly in terms of a set of stabilizers. There are again two types of stabilizers. The first is a vertex stabilizer. This is a product of LG and RG around a vertex. The assignment of LG and RG is determined by the orientation of the edges. So LG if the edge points away from the vertex, RG if the edge points towards the vertex. Note that in general, these do not commute, because in general, we can consider a non-abelian group. They'll commute at neighboring vertices, but they'll fail to commute at the same vertex. AVG and AVH might not commute. The second type of stabilizers that we have are plaquette stabilizers. These project onto states such that the product of group elements around the plaquette is equal to 1. Here, this product is taken according to an ordered path, and whether it's G or G inverse depends on the orientation of the edge. So here, this checks G1 times G2, but here it's G2 inverse. G3, it's opposite. We'll go counterclockwise around the plaquette. If this counterclockwise path is aligned with the orientation, it's G. If it's anti-aligned, it's G inverse. So that's why it's G1, G2 bar, G3 bar, G4. The code space is then the set of states that are invariant under all of the vertex stabilizers and all of the plaquette stabilizers. In gauge theory language, AG can be interpreted as a gauge transformation. So being invariant under the gauge transformation says that we have a gauge invariant state. Being invariant under the plaquette operator can be interpreted as the state being flux-free, so there are no fluxes. So the code space consists of gauge invariant flux-free states. And I'll prove in a moment that the dimension of the code space is the order of G. But let me pause for
Can
a
I ask a
moment.
question?
Yeah, please.
Sorry, are there truncated versions of the plaquette operators here as well?
Yeah, I was pressed for space and I put this small, similar for left and right boundaries.
Okay,
So there's,
sorry.
yeah, no, thanks for asking. You do multiply just 3 group elements near the boundary.
That's similar to setting, equivalent to setting like one of the edges as identity, I guess.
Exactly. Yep. You can imagine that
Got
there are just identity edges on the boundaries here.
Gotcha. Thanks.
Yeah. Thanks for
Let's
asking. Yeah.
what property of the group G have to determine the whether the surface code support non-qualified gates?
That's a good question. So it's a bit difficult to answer that question because what we mean by Clifford or non-Clifford depends on our encoding. So we ultimately need to be able to transfer our information from Z2 surface codes into this non-abelian theory, then back to Z2 surface codes to make an assessment of whether it's Clifford or non-Clifford. So I don't know how to just say in general this group has Clifford or non-Clifford. I need to also consider transferring information from some abelian surface codes, or I need to tell you what are the Pauli operators so that I can define Clifford and non-Clifford.
Okay, I see. Thank you.
But yeah, that's a very good question. I don't, for all the examples that I've considered now, I've only considered very simple groups. They admit a non-Clifford operation. But I'll specify the class of groups that I'm considering, and I think you have to get pretty exotic groups to fall outside of this class.
Mhm. Thank you.
Yeah.
Yeah, Tyler, I have a related
Yeah.
question. So you
Yeah.
emphasize this is from the standard, this is different from the standard non-abelian topology order, like we can use S3 to perform universal unitary gate using the anion braiding. So
Yeah.
you don't follow the traditional rule.
Yeah.
So yeah.
Yeah. Oh
So
yeah,
in this case,
this is build. Yeah, this is
does
building off
S3
of.
work?
Sorry, go ahead. Go ahead. Sorry.
So I don't say does S3 like default work here?
Yeah, S3 and D4 are both good examples. I'll use D4 as an example later in the presentation.
Okay. Any concrete example, like what kind of group doesn't work here?
What kind of group doesn't work?
Yeah.
Yeah, let me get to the elementary operations, and then I can explain the limitations on the groups that we can consider. But A5 is fine, so it doesn't need to be solvable.
Oh, okay. Yeah. Thanks.
Yeah, but to make that statement a little more, to make the statement more rigorous, I'll need to get a little further into the text, or into the presentation.
Tyler, before you do so,
Yeah.
I also want to follow up. Do
Mhm.
you mean whether this group surface code works still depends on how you connect the Z2 surface code and the group surface code?
Right, yeah. So if your question is, can it perform a non-Clifford operation? Non-Clifford isn't well defined unless I also tell you what are the Clifford operations, and that requires telling you what are the Pauli operations. So it's pretty natural to define Pauli operations in an abelian surface code. So if once you have those Pauli operators defined, now you have to relate it to my non-abelian theory, and then maybe that involves transferring the information into the non-abelian theory. Then we can talk about whether it's Clifford or non-Clifford.
Okay, thanks.
Yeah. Okay, good. Yeah, thank you for the questions. If I don't finish the presentation, that's fine. At the end of the talk, the paper will appear, and so it's the continuity is all good. Okay, so what I'd like to do next is I'd like to prove that the code space has dimension order of the group G. And the way I'll do that is I'll consider the set of flux-free states. These are group basis states, so it's just a configuration of group elements on the lattice, such that there's no flux. The BP, the plaquette term, is stabilized, is satisfied. So here's an example. This is a configuration of group elements. You can check by multiplying the group elements around a plaquette. There are no fluxes. This is, however, not gauge invariant. It is not invariant under applying the vertex term. But what we'll do is we'll organize these flux-free states into gauge equivalence classes. We'll say two flux-free states are gauge equivalent if there exists some product of gauge transformations that maps one flux-free state to the other. So for example, this flux-free state is gauge equivalent to this flux-free state. I can apply a vertex term here and here, and that removes these loops. In order to form code states, we can take an equal amplitude superposition over flux-free states over a gauge equivalence class. These will be flux-free because it's a superposition of flux-free states, and it's gauge invariant because we include all of the configurations in the same equivalence class. These furthermore form a basis for the code space. They span the code space since every flux-free state belongs to some gauge equivalence class. That implies that the code states must be superpositions over gauge equivalence classes. These are also orthogonal, since distinct gauge equivalence classes will give rise to orthogonal states. So this forms a basis. And that means that all we need to do now is count the number of gauge equivalence classes. So here's what I'll do. I'll consider a general flux-free state. This is just a configuration of group elements. There are no fluxes. And I'll argue that I can put this into a canonical form, which allows me to easily label equivalence classes by some nice representative state. What we'll do here is we'll try and push all the group elements to the right by applying gauge transformations. So first I'll apply a gauge transformation AG1 here. This acts with G1 inverse at this edge. So it'll move the configuration, it'll move that group element to the right. Then I'll proceed across this top row, apply AG1, G2 here. Then I'll move the group elements further. And I can go all the way across the top row, end up with some group elements on these vertical edges and an element G on the rightmost edge. I can do this in all the rows. So let me go ahead and do that. I apply gauge transformations in all the rows to move the group elements to the right. Now we use the fact that this state is flux-free. Since it's flux-free, the plaquette term is satisfied here, which means that the product of group elements around this plaquette should be equal to 1. That implies that G6 tilde was 1. Okay, now I can go to the next plaquette, and that implies that G7 tilde is equal to 1. We can go clear across the row, and in this last plaquette, we find that going around this plaquette, G times H inverse has to be equal to 1. If G times H inverse is equal to 1, that means that G is equal to H. I can do this in all the rows, and what I end up with is the messy configuration we started with is gauge equivalent to a configuration with the same group element on all the edges on the right. This is a representative gauge fixed state, and it's labeled by a unique G in G. It's unique for a reason that isn't important if it's unclear, but you can compute the oh shoot, what's the word? Holonomy, sorry, the holonomy across this patch, and that's gauge invariant. So this labeling by G is unique. So we see the gauge equivalence classes are labeled by elements of G. So here's a gauge equivalence class labeled by G. It's represented by this configuration where all the group elements are on the right. This forms a basis. So the dimension of our code space must be equal to the order of G. We'll label the basis states by the elements of G, and I'll put a subscript L here to remember that they're the logical states. So what this state is explicitly is a sum over flux-free states in the gauge equivalence class labeled by G. And moving forward, it will be convenient to work with the gauge fixed states as opposed to this superposition. So we'll just look at this nice representative state where all the group elements are on the right. What I'm going to do next is start introducing elementary logical operations for the group surface code. But let me pause here and see if there are any questions about this argument. Okay. There are three types of elementary logical operations that I'll introduce. The first are transversal gates. Transversal gates are implemented by a product of single-site unitaries on every edge. Extend and split. This allows us to take two group surface codes and merge them into one group surface code. It allows us to transfer information from Z2 surface codes into non-abelian surface codes. And then finally, preparation and readout. Let's start with transversal gates. The first gate that I'll introduce is a transversal left logical multiplication. It's represented as such. I apply LG on all of the leftmost edges of the lattice. The first thing to check is that this commutes with all the stabilizers. It commutes with the vertex stabilizers by virtue of the fact that LG and RG commute. So this vertex stabilizer, they act with RG to the left, LG and RG commute. So this commutes with all the vertex stabilizers. It also commutes with all the plaquette stabilizers. It doesn't create any fluxes. And what I'll argue is that applied to the logical state labeled by H, what this operator does is it takes us to the logical state labeled by GH. You can see that explicitly by considering a nice representative state for the H logical state. LG acts by left multiplication on the leftmost edges with G. So that takes us to this configuration. And by applying gauge transformations to move the G variables to the right, we end up with the state GH. And that illustrates this equation here. Similarly, we can define a logical right multiplication just by acting with the right action by G on all the edges on the right. Acting on a state labeled by H, it takes us to HG bar. So explicitly in terms of a gauge fixed state, a representative state, we take a configuration that has H on the rightmost edges, we just insert G bar. The next transversal gate that I'd like to introduce comes from group automorphisms. So phi here is an homomorphism from G to itself. We can define a unitary operator that implements this automorphism. So it acts on a group basis state labeled by G and takes you to the state labeled by phi of G. It just permutes the group elements. The way we can implement this at the logical level is by applying U phi on all of the edges. The first thing to check is that this preserves the stabilizer group. It does not commute with all the stabilizers, but it permutes the stabilizers amongst themselves, so it preserves the stabilizer group. And what I'll illustrate here is that at logical level, it takes logical state labeled by G to logical state labeled by phi of G. So acting on the gauge fixed states looks something like this. We apply phi G or U phi on all the sites, on all the edges, and we end up mapping the configuration G on the right to the configuration with phi G on the right. Now let me give an example illustrating how these transversal gates can implement a non-Clifford operation. So consider G equal to D4, the symmetries of a square. I'll represent D4 as follows. It's generated by A, B, and C. A, B, and C all square to 1. And the only really non-trivial relation here is that if I conjugate A by C, it produces a B. This suggests that D4 can be written as a semidirect product of Z2A times Z2B with Z2C, where the semidirect product notation just captures the fact that C acts non-trivially on A by mapping it to AB. We know that we can label the logical states by elements of the group. So any element of the group can be represented as A times alpha, A to the alpha, B to the beta, times C to the gamma, where alpha, beta, and gamma are 0, 1. So this suggests that the code encodes 3 logical qubits. Now we can consider left and right multiplication. If we act with left multiplication with A, it introduces an A on the left and takes us from alpha to alpha plus 1. So this acts as x1 on the logical level. More interestingly, we can consider LC times RC acting on this state. So it inserts a C on the left and a C on the right. We can use the group relations to move the C on the left past A. We'll pick up a B depending on alpha. So it maps this to A to the alpha, B to the beta plus alpha, C gamma. That means that this acts as a CX12. It flips the second qubit based on the state of the first qubit. Okay, even more interestingly, we can consider the group automorphisms, a particular group automorphism, D4. So here's one automorphism of D4. What it does is it takes the element A, maps it to C, B gets mapped to itself, and C gets mapped to A. Now applied to a logical state, it'll just swap A and C. That's what I've done here. I've just swapped A and C. In order to put this in the form where we have A, B, C, we have to move C to the alpha, past B to the beta, and A gamma. And here's what that produces. So what's happened is alpha and gamma have been swapped, and the second qubit has been flipped contingent on the state of A and C. So this acts as a swap on the first and third qubit and a controlled X gate which with target qubit being the second qubit. This turns out to be a non-Clifford operation. So if we were able to transfer our information to the D4 group surface code, then we could apply this group automorphism to enact a non-Clifford gate. And that would be enough to supplement our Z2 surface code and perform universal computations.
Hello. In
Yeah.
this example, some very specific properties of the default group are used. Then, how do I see how general this is?
What do you mean some specific properties of the D4 group are used?
Like the group structure, not only that you can organize the logical states in this alpha, beta, and gamma way, but also the fact that you are doing it in this particular way. Because the usual way I think of D4 is as the as the symmetry of the square of a square, with two generators. One is the four-fold rotation, and the other is some reflection. Before seeing your way of writing the group elements, I wouldn't even think of writing the group elements in this way.
I see. I see. Yeah, I wrote it in this way so that we had 3 qubits. But we could use another representation of D4, which is Z4 semi-direct product with Z2. And in that case, we also can get non-Clifford gates. Well, actually, I'm not sure. I'm guessing that is non-Clifford. I don't know what happens on the four-dimensional qubit. I haven't checked this. But in general, when you have this semi-direct product structure, the lowest level here, these act as Pauli operators. When you do left actions, this acts as Pauli operators. These, in the next level, they act as Clifford operations. That's why we have this CX1, 2 here. And then you could imagine adding another layer, and that implements this group automorphism, and that's what does the non-Clifford gate here. So yeah, so this lowest level Pauli operations, and this next level that's defines here. Here I'm doing some inner automorphism where I'm conjugating the group element by the element here, and so that will implement some Clifford gate. And the next level, or using an outer automorphism, it goes one step higher in the Clifford hierarchy.
So do you mean you have a general criteria as a sufficient condition for this framework to work? Meaning if some
I don't remember what sort of general statements we can make about semi-direct products, but I would be willing to go out on a limb and say that when you have this semi-direct product structure and it's like sort of a non-trivial semi-direct product, sufficiently non-trivial semi-direct product, then each successive semi-direct product takes you one higher level of the Clifford hierarchy.
I see. Mhm. Thanks.
Yeah.
Tyler, I have a naive
Yeah.
question. So I want to know practically, is this useful? Because if we just try to use 3 qubit, try to represent the default, it's kind of we already assume we have the ability to perform this kind of LG and RG, which already require a non-Clifford gate. But in reality, we don't have any natural system which has the default qubit. So I wondering, it looks like just you try to stay the same thing using the other representation, but practically it's still the same difficulty. Like it doesn't help us to apply CCX on the superconducting device.
I see. You're saying, yeah, that's right. So if you wanted to measure the vertex stabilizers of D4, you would need to, and you're representing it using 3 qubits, then you would need to implement CCXs.
Right. So it doesn't help us to reduce the difficulty in the experimental device, right?
Yeah, that's fair. Maybe it's a hardware dependent statement. I am not too concerned about the implementation of the stabilizers at this point, but you're right. Yeah,
Yes, I see. So the point here is assuming we have some already default QD, which can be naturally implemented on some suitable physical system, and using this default system is easier to implement those kind of gate.
well, so yeah, you could use an 8-dimensional QDIT, and construct this as long as you can, measure those stabilizers naturally on your 8-dimensional qubit. But what I am imagining here is that I have 3 qubits in the system, that LG and RG will look like some product of X's and C naughts. So the stabilizer is still a Clifford operator.
I see, but
But if you want,
Clifford in default sense.
no, Clifford on qubits.
Oh, okay.
Yeah, yeah.
Oh, I see.
Yeah, I can take that 8-dimensional Hilbert space and break it into 3 qubits. And then I can ask, well, what is the representation of LG and RG on those 3 qubits? And LG, I don't know, it depends on what group element I take, but it's either X or X times C naughts.
Oh, okay. Thank you.
Yeah.
If the order of the group is not a power of 2, then we cannot decompose them just into qubits, right?
Yeah. Well, that's right. Or you can impose some constraint and like turn 2 qubits if you want into a qubit.
So you mean ultimately, even if I, for example, have a qubit, I want to add some constraint to reduce it to a qubit, or the other way around?
So, sorry, I was saying you were saying if the order of the group is not a power of 2, I can't represent it on qubits. And I guess that what I was saying is um, you still can represent it on qubits. You might just not be using your resources efficiently. Like I
But
can represent a qubit
sure, sure.
on 2 qubits if I want to.
Yeah, yeah. For example, I'm asking, suppose the group is S3
Hmm.
with 6 elements.
Yeah.
Then using this framework, the number of logical states will be 6. Uh,
Yes. Yeah.
then you cannot organize them as an integer number of qubits.
Yeah. There you could have a qubit and a qubit if you wanted.
Then when you talk about Clifford,
Mhm.
Clifford meaning what?
Yeah. So I'd have to tell you what I mean by a Pauli operator on a qubit.
Uh-huh.
But this is quite naturally taken to be just a clock and shift operator.
Okay, okay.
Yeah.
Thanks.
Yeah, thanks. No, those are good questions, and there's not much I can say about hardware implementation of these codes. At this point, it's fairly abstract. Okay. I'm somewhat pressed for time, so let me unfortunately make these next steps somewhat schematic. But the next logical operation that I'm going to introduce is an extension and a splitting. This is what allows us to transfer information from abelian surface codes into non-abelian surface codes. And at a high level, what it does is it takes an H group surface code, a K group surface code, and turns it into a group surface code for a larger group. And in general, we can extend H and K group surface codes into a knit product of H and K. If I had converted my time zones correctly, I'd explain what a knit product is. But for the purpose of this talk, I'll just consider a semidirect product. That's a special case. But this is what allows us to extend to non-abelian groups. For example, we can take a Z2 cross Z2 group surface code and a Z2 group surface code and use this extension operation to convert it into a D4 group surface code. Um, I'll skip a definition of a semidirect product here. Here's the strategy for extending an H and K group surface code to an H semidirect K group surface code. You start with 2 independent patches of surface codes. You overlay the two, and on their interface, you measure the stabilizers of the H semidirect K group surface code. Then you continue to grow the H semidirect K group surface code by measuring stabilizers until you've converted the whole patch into the H semidirect K group surface code. And for technical reasons, let me just note that it's important that H starts to the left of K. To show this explicitly, Here are two group surface codes. They overlap each other. You can measure vertex stabilizers. Depending on the measurement outcomes, you may need to make corrections. Let me just, for simplicity, assume that all the measurement outcomes are +1. Then we'll have successfully projected into the gauge invariant space of the H-symmetric K group surface code. So we have gauge transformations here in H-symmetric K. We can use those to then move these H elements to the right by applying some gauge transformation. Then we'll continue to measure vertex stabilizers to convert this into a larger H-symmetric K group surface code. This gives us new gauge transformations, and we can gauge fix by applying some gauge transformations and move the H's to the right. And eventually, we'll turn the whole thing into H-symmetric K group surface code. And at the logical level, what we've done is we started from a state labeled by H and a state labeled by K and turned it into the state HK.
Tyler, I have a quick question.
Yeah.
Does
Yeah.
this require post-selection, or you can do some error correction if the measurement is not identity?
Yeah, no, it doesn't require post-selection. What happens here is the measurement outcomes are some charges that can be condensed on the interface. So there may be some charges here. So if your measurement outcome is not +1, that means there's some charge sitting here at this boundary between H-symmetric K and the K group surface code. You can just push those charges into the boundary. So there's some procedure for cleaning up the charges that are created throughout this process. There's no post-selection needed.
I see. Thank you.
Sorry. Is local Hilbert space enlarged?
The local Hilbert space is enlarged. Yeah, that's right. I implicitly was adding ancilla so that I could measure the H-symmetric K group surface code stabilizers.
Oh, thank you.
Yeah. Thanks for clarifying. Okay, that's extension. Next is splitting. This takes a larger group, let's say an H-symmetric K group surface code, and splits it into an H group surface code and a K group surface code. So we can split to get back to our abelian groups. So for example, we can take our D4 group surface code and transfer the information back into the Z2 cross Z2 and Z2 group surface codes. The overall strategy is to eject a K group surface code from the H-symmetric K group surface code. And we do that by adding ancilla, measuring the K stabilizers, and growing a K group surface code out of the H-symmetric K group surface code. Then we make measurements of the H-symmetric K group surface code to turn it back into an H group surface code. In this case, K was ejected to the right, but similarly, you could eject K to the left. We can see what this does at the logical level by considering the gauge fixed states. Suppose we start with an H-symmetric K group surface code in the logical state represented by the configuration with HK on the rightmost edges. Then we eject a K group surface code by adding ancilla, measuring the K vertex terms. Again, we might need to make some corrections. That creates this K group surface code. And then we can we can apply a gauge transformation to move the K group elements to the right. And we can repeat this process by adding ancilla, measuring vertex stabilizers, using the gauge transformations to gauge fix. Then eventually, we'll have an H-symmetric K group surface code, a K group surface code. We measure out the additional K degrees of freedom on the right. That just takes us to an H group surface code and a K group surface code. At the end of the day, it takes a state labeled by HK and splits it into H times K. If we eject the K group surface code to the left, then instead we're left with H conjugated by K. And so it can perform the conjugation. The conjugation of H by K may be non-trivial, these semi-direct products. So it takes us to some potentially different value in H here. Before I move on to preparation and readout, are there any questions about extension and splitting?
Could I ask a question for the general case, which you didn't comment on, but I was curious. So in this knit product thing that you mentioned, does this include non-split extensions as well, or just like split extension?
Yeah, so it includes A5. A5 is a knit product of Z5 and A4. It does not include central extensions generically.
I see. Does it have any
Yeah.
relation to matched pairs of groups?
Yes, I think so. I think so. The definition is a group G is a knit product of H and K. If H and K are subgroups of G, the intersection of and K is trivial, and every element of G can be uniquely labeled by HK.
I see. Okay, sounds very similar. Look into it.
Yeah. It has many names. It's also the bicross product or the Zappa-Zip product or the
Okay.
generalized product. Yeah.
Okay, cool. Thanks.
Yeah. Okay, let me briefly talk about preparation and readout. Preparation is straightforward. We'll start with a small group surface code, add some ancilla to grow it. There are some charges that will appear. There are some violations of stabilizers generically when you make these measurements, but you can remove those by just dumping them into the boundary. Readout is fairly simple. You measure all of the edges in the group basis. This just leaves you with some configuration of the group elements. Okay. Now we have all our elementary logical operations. And what I'll do is I'll compose those together to form more interesting gates. In order to do this, it's useful to go from space to space-time and from a discrete picture to a continuous picture. In the text, which you can find maybe now on arXiv, we do this via a tensor network, a sort of generalization of ZX calculus to groups. But for the purpose of this talk, let me just go from the lattice to the continuum using this squint operation. You just squint at all the diagrams that I've drawn so far, and it looks like a picture in the continuum. And in order to make this a space-time picture, here I'll represent the identity, or just an evolution, Euclidean space-time evolution of the group surface code by this empty block, where the gray surfaces are the rough boundaries. And in the picture where we have some gauge fixings, you can think of this as at each instance in time, it's a sum of membrane configurations where at each instance of time, I've gauge fixed. This is a possible gauge fixing of my state. I can also interpret this as an operator, and it's the logical identity. So I take my state, I put it in at the bottom of this operator, and what it spits out is an equal amplitude superposition of configurations in the same gauge equivalence class. Now I can represent all of those elementary logical operations in space-time. Here's a representation for the left logical action. In this case, membranes can end on this defect. There's left action, right action. The group automorphisms logical operation is just a membrane in space-time here. This is what extension and splitting look like. Here we have H and K being merged together into H semidirect K. And these are interfaces between H and K and H semidirect K group surface codes. This is what preparation and readout look like. And we have our space-time building blocks now that we can glue together to perform operations. Okay, Let me show you just a couple examples here before I run out of time. This first operation we're referring to as a slide operation. It's a split. It's an extension with h on the left, k on the right, and then a split into kh. And notice that k is on the left at the end, it's on the right at the beginning. So it's like this k group surface code is slid across the system. And this reproduces some of the results that have appeared earlier in the literature. So as an example, we can consider what happens with D4. Our initial state is maybe A to the alpha, B to the beta on the Z2A times Z2B patch, and C gamma on the Z2C patch. After extension, we just multiply them together in the D4 group surface code. And then when we split, since the Z2C is on the left, we conjugate we conjugate the Z2A times Z2B element by C gamma. Moving C gamma through here produces an extra B depending on the state of gamma and alpha. This implements a logical controlled NOT gate. One can also perform magic state preparation by a similar protocol. Here, though, we initialize the states, say in the plus state or the plus 0 state, and we make a measurement in the x basis. What it outputs is some magic state. We can make this more resource efficient using the fact that we can deform these pictures and just shoved these legs into the diagram. And this reproduces results that have appeared in literature. And let me conclude here. Sorry, this is pretty sketchy, but here's one last diagram. I'll start with K Z2 surface codes and some unspecified group K here. We can make a judicious choice of K so that we're able to perform arbitrary reversible classical gates transversely in the group surface code. So you transfer your information of Z2K into this funny group surface code, and then you can transversely implement any logical permutation of the logical bit strings, and then you can eject the information again. So the main takeaway here is that you can start with Z2 surface codes, perform all of your Clifford operations in the Z2 surface codes, transfer your information to the G group surface code. You can engineer this group for a desired non-Clifford gate, and then transfer your information back into Z2 surface codes. And I'll conclude here just by listing some future directions. Thanks.
Thank you very much for the very interesting talk, Tyler. Any further questions?
Yes, hi. So how can I see that this is sufficient for universality? For example, if I want to perform maybe a phase gate, can I see how can I implement this gate using your protocol?
Yeah, no, that is maybe difficult to see. It turns out that there are some remarkable set of gates that are universal. For example, just a Hadamard and this controlled NOT gate is universal. And that might look kind of funny because there are no complex phases that appear here. But what you can do is you can use an ancilla to keep track of the real and imaginary part of the state. So I don't know the proof, but there are certainly proofs that you use something like CCX and supplement that with the Clifford operations, and that allows for universality.
Thank you.
Tyler, I also have a question.
Yeah.
Which you already commented on and Yuan asked. So in the introduction, you mentioned here you are using non-abelian topological phases in certain way, but different from how people previously used to do topological computation. And you said the reason was practically what you do here may be technically easier. You, then later, when you answer the Yuan's question about practically how easy it is, then you said at the moment you don't really have assessment of that. So I certainly think the ability, the possibility of doing this and the whole structure of these different theories, how they are connected and how we can grow one, how we can extend, how we can split, these are all very interesting. But suppose I really ask you to assess how practical this is, what would you say?
Well, that's fair and a difficult question to answer. But Quantinuum's already prepared a D4 topological order. It's not fault tolerant. And I think what the challenge is making that fault tolerant by repeatedly measuring at all the vertex terms. So I think that's an outstanding problem. I don't claim to have an answer of how to efficiently measure the stabilizers here. But if you don't want to think in terms of active error correction, maybe it's interesting from the standpoint of maybe you have some Hamiltonian that realizes this topological order, and you may tune some parameter in your Hamiltonian to go from your Z2 surface codes to your non-abelian topological order. Then you can implement some transversal gate if you'd like and switch back. It may be just a way to perform operations with topological qubits too.
For the continuum, you mean the one on Kagome lattice?
Yeah.
Yeah, maybe a related question is, in your description of the topological phase, you are using a particular realization of it, a particular microscopic realization where the local qubits have the basis of the group elements. But in the continuum realization of the D4, each qubit is really a qubit, and it's a D4 for a kind of a non-trivial reason. Then, really, in that particular microscopic realization, would you imagine one has to do a lot more work to implement the whole thing?
In which realization takes more work? What do you?
The realization using just the qubits on Kagome lattice instead of
I think
using
that
eight-dimensional qubits.
I see. Yeah, naively, the complexity of the Hamiltonian terms in terms of qubits look the same. There's a product of Pauli X operators and some CZs, or product of Pauli X operators and some C naughts. So they look very similar represented on qubits.
So it doesn't matter that the Hamiltonians are not commuting projectors.
Yeah, it's not essential that the Hamiltonians are commuting projectors.
Mm.
But I guess I don't really know how to assess the complexity of the stabilizers. I guess that's what you're asking about. But at least naively, at surface level, the Z2 cube twisted quantum double stabilizers look very similar to these D4 group surface code stabilizers when represented on qubits.
Okay.
Yeah.
Any other questions?
I had a question about your last point about the half algebra.
Yeah, I don't have anything too intelligent to say about this, but yeah.
Just wanted to maybe make a comment. This bycross product also exists for half algebras. This kind of like knit product. Wonder if we can just plug and play. Yeah, this is something that mathematicians have studied.
Oh, that's very cool. Yeah, that's nice to know. Yeah, I think this is kind of an ambitious last bullet point here because ultimately what makes the group surface codes nice is that you can relate them to some abelian group surface codes, do some computations in the abelian group surface codes, and transfer information as needed. With a general half algebra, I don't know that you have that luxury that you can transfer information from your Z2 surface codes, for example.
Right. The one example I was thinking of with H8, it's an eight-dimensional half algebra. That can be thought of as a co-cycle version of this bycross product. So it's some more data, not just a bycross product. You can think of it as like a central extension analog for half algebras. But you did say that central extensions are beyond the current construction you have. So I don't
Well, so we
know for
can we
sure.
can talk about central extensions. We've worked this out on paper, but what happens is
Ah,
that some of the information is killed when you transfer into the centrally extended group. So it's not clear how this is useful yet.
okay.
Yeah, yeah.
Thanks.
Yeah, thanks. That's interesting to know.
Tyler, I have an additional question. So what's the benefit of choosing the surface code instead of the Torah code? Because for surface code, we need to implement different gate boundary. So I will expect it's much harder to construct compared to just periodic boundary condition. But there's also benefit like easy to implement on physical device, and you can use this kind of a lattice surgery try to connect different page. So is it the main reason why you choose the surface code with open boundary?
I would say that the main reason that we chose the surface code is that there's this group interpretation of all the operations. So this is really just a quantum double model. But the reason we're calling it group surface codes is because you don't have to invoke all the quantum double mathematics. I never have to say, irreducible representations of the centralizer of an element of the conjugacy class. I can talk purely in terms of groups.
But same for a torus, right? You can apply the centric, try to organize the configuration into some non-contractible loop.
Yeah, so the degeneracy on a torus is more complicated. Like for D4, the degeneracy on a torus is 22.
Oh, okay. It's not like A times A or something.
No, it's not that simple. Yeah, yeah,
I see. Yeah. Yeah, that's a good point. Thank you.
yeah.
Hello. Hello. Uh,
Hey,
I have a question about the first point about decoding and verifying for tolerance. Because
yeah.
in this system, if we implement the system by qubits, the native physical gates on the qubits is non-Clifford. So if you want to simulate, for example, a circuit level, if you want to implement a circuit level simulation, you will encounter many non-Clifford gates. But from another perspective, the logical non-Clifford gates is only one. So how would you expect the complexity of this simulation or verifying the fault tolerance?
Ah, that's a good question. Decoding group surface codes and non-abelian topological errors or these C2 cube twisted quantum double models is an open question. We introduced some language of tensor networks in the paper, which I think are valuable because it mirrors ZX calculus, which has been useful for Z2 surface codes, where you can decompose your noise into Pauli operators, and then you can imagine pushing these Pauli operators through your circuit. Here, you could decompose your noise into left action and right action and something that's some operators that are diagonal in the group basis. And these have some nice pushing through relations in the tensor network diagram. So that might be one first approach, but that is a tough open question.
Yeah, but if you can really circumvent the exponential complexity by this decoupling it to the group basis, does it violate that this scheme is universal?
I'm not sure I see um, the inconsistency here. I guess I'm not simulating what's happening at the logical level. I'm simulating some errors that are appearing, and then I'm removing those errors. So I would agree that there'd be some issues if we were trying to simulate the logical state. But when we're talking about fault tolerance and decoding, all we need to check is that there aren't any logical operations that are applied via our errors and corrections.
Yeah, but because I suppose the logical operator you implement is also just in the group basis, or is there any misunderstanding?
Um,
And on the logical level, what you do is also manipulation in the group basis.
so all of the examples that I showed, I used the group basis and I showed the logical operation on a group basis state. but generically you'll have some superposition of those group basis states. Does that answer your question? I'm maybe not sure I understand.
Maybe. Yeah, I think it's maybe it's just an open problem. Yeah.
If I just start with a group basis state, it's easy to track what the logical operations are doing.
Yeah,
But when I
see.
have some more complex state, that's the superposition of group basis states, then there may be some difficulty in tracking the logical state.
Okay,
once I start composing these things.
I see.
Yeah, and insert some Hadamards.
Okay, I was just reminded. Some time ago, there was another paper from Boulder and other people, including Andy Lucas, with a similar title. That what's the relation between your work and that work?
Yeah, that's a fair question. So they talked about quantum double models on two-dimensional CW complexes, and they computed the degeneracy of the quantum double models on these general CW complexes, and they put some distance bounds on them. We're more concerned in this work on implementing logical gates and showing what logical gates are possible.
I see.
The overlap would be the calculation of the ground state degeneracy on a patch. That's the overlap, I suppose.
I see. Not much.
Yeah, no. Different objectives entirely.
Yeah, thanks. Any other questions? Okay, if not, thank you again, Tyler, for the very interesting talk.
Yeah, thank you all. The
Yeah.
tough questions.
Yeah, we will not tough, I guess, friendly questions.
Yeah.
So I'll end the Zoom meeting now. See you.
See you later.